Congratulations on making it to the last day. It's still a full room, so you're all very dedicated. That's impressive. So what I wish I could do is tell you that I'm going to tell you everything that you need to know about SIENA models, but unfortunately that would take us probably another 2 weeks to get through. So my goal today is to talk about more conceptually what is it that a SIENA model can do, and then in the lab part of today, get into enough of how we actually work with longitudinal network data within SIENA so that if you're interested, you can start to at least understand the process of it a little bit further. All right, so I want to start off with a question. Okay, so here we have some data on high school students and their smoking behavior. You're familiar with AdHealth? Yeah, by now? All right, so this is Jefferson High. And here we have nodes shaded by their smoking. And it's not a great image. I'm embarrassed to put this up here, but I have it already. You can kind of see there's some clustering on smoking over here, the darker nodes, fewer smokers over here. You really can't tell, but smokers are a little bit popular in this school. So if we look at the correlation between smoking and in degree, it's positive, it's significant. And there's also significant clustering on smoking. So if we calculate an odds ratio, odds of choosing someone who's similar in smoking versus someone who's dissimilar, we see a positive and significant odds ratio. Okay, so we have smoking homophily, we have smokers who are popular, and then the question that we all want to know is why? Why is that? Because we think that's important and that the network has something to do with maybe perpetuating smoking, and we want to do something about that. Okay, so let's break this down into a little bit simpler question. Okay, so here we have at time t some kind of homophily on smoking. We have homophily on smoking, and we want to know what brought that about. What happened before time t? Okay, and we've got two processes that could have occurred. It could have been this peer influence process where adolescent friendship dyads were initially dissimilar and over time switched behaviors to become more like their friends. It also could have been friend selection, right? It could have been that these similar people were not friends early on, but became friends over time. Okay, and so we've got these two competing explanations for what it is that we observe in our network. Okay, this is the case of homophily, and oftentimes we're thinking about homophily, but there are other kinds of correlations or associations between the network and behavior that we might want to investigate. Okay, so here is an example of smoking-related popularity, where the only smoker in the network receives the most, in fact, all of the incoming ties. Okay, so how do we get to this point? Well, it could have been that the network, where B is more popular, led B to start smoking. B's got more autonomy, a little more secure. B can take on risky adult-like behaviors. Or it could have been that B was already a smoker, and something about smoking, something about kind of acting like an adult, rebelling, leads to popularity. Okay, so again, we've got two different explanations for what could have happened here. We want to try to parse between these two explanations. Okay, now, in trying to infer that the network is the source of behavior change, we want to control for selection on that behavior. Okay, that part I hope is fairly obvious. But we also want to, in modeling the network and controlling for selection, control for a number of other things as well. Okay, so we want to control for similarity on things that are related to the behavior. Okay, so smoking and socioeconomic status are related. Oftentimes kids are selecting friends based on similarity in socioeconomic status, either directly or indirectly. So if we don't account for that selection based on socioeconomic status, we may not be picking up all of the selection processes. We may be inferring it is a product of smoking and not SES. We also want to control for other kinds of processes by which selection occurs. Okay, we talked about some of these, I know, during the week. These things like reciprocity and transitivity can actually amplify the amounts of homophily in the network. Okay, so let's say we have one person in this network who just really loves homophily, right? So they want friends who are similar. Everybody else is indifferent. Okay, no one else cares, but that person selects friends based on homophily. When we see other friendships form through these other processes, for instance, a reciprocated friendship here, a transitive friendship here, it's those other processes that are driving friendship change, but they're still producing ties that are homophilous, ties between people who are similar. And so we want to account for these to get a better estimate of how much selection on that attribute is driving the network, to also model, to get a good model of how the network changes over time. Okay. All right, so when are we going to use a SIENA model? Okay, questions about how behaviors change. So peer influence is what comes to mind oftentimes. That's where most of the research using SIENA is. We could also use a version of SIENA for diffusion to look at how behaviors spread, how kind of new adoptions spread throughout a network. We can also use it to think about how the network structure itself changes over time. So questions about how health might drive withdrawal or exclusion from a network. So having a health condition such as obesity leads to stigma, may be excluded from networks. We can model that kind of process. We can model withdrawal such as through depression. And more generally, we can get a better understanding of how is it that the networks that we think influence us and affect our health and other kinds of outcomes, how is it those structures themselves come into being? Okay? And then we can also use SIENA to look at how these selection and influence processes accumulate over time. We've got a feedback process here, fairly complex kind of reciprocal cycle of effects. We can look at how those accumulate over time and affect things like health disparities, correlations between different attributes and health outcomes, how those might change, and how we might be able to change those by either under different scenarios of selection or different kind of processes of influence. Okay, so that's the goal, is to be able to do all of these and a lot more. Okay, I wanted to take a minute to just point out a little bit how these models differ from some of the other models that you may have heard about this week. Okay, so briefly, most of the models that we've talked about either look at an individual attribute and how is it a network contributes to changes in an individual attribute. Most recently, I think the network autoregression models in the lecture on diffusion yesterday. We also have models that look at network change, okay? And we talked about QAP, talked about ergoms, okay? With the SIENA model, we're bringing both of those together, okay? We're looking at both of those simultaneously, how the network contributes to individual outcomes and how individual outcomes or behaviors then feed back into the network. So we're doing both of these things, okay? Now, I wanted to take a minute to try to distinguish SIENA from a ergom or temporal ergom approach, which, have people heard about temporal ergoms? Okay, a couple of people, all right. I know we heard about ergoms yesterday, but there's an obvious question, well, they're both modeling network change over time. Does it matter which one we use? This is still an area where there's a lot of development and actually a lot of active research trying to understand what are the differences and kind of when is one more appropriate than the other. So I'll touch on just a couple of things that I think are important to keep in mind when making that kind of choice. So an ergom model, and there's a variety of different kinds of ergom model, but really the goal of the ergom model is we're modeling the network observed at time t, and we're using some functions on t-1 to predict that network. So we're looking at the discrete change from t-1 to t. Okay, so at time t-1, we've got some ties. We're going to use those ties to predict which ties persist. Then we're going to look at some structures that emerge net of those ties. Okay, where you can think of it again as regressing time t on time t-1 and adding some other predictors to pick up which ties change during that duration. Okay, in some ways, very, very straightforward model. Picking up all of the dependencies over time is a little bit more complicated. This is a SIENA lecture, not ergom, so ask me about that later, and I'm happy to talk about it. There's actually a slide way at the end that does, but it gets at dependencies very differently. Okay. SIENA model, by contrast, is takes the time t-1 network, and we're trying to get to time t. We're going to assume that there are numerous unobserved intermediate steps by which the network changes between those two observations. Okay, so it's a continuous time model that goes through these we call them microsteps, one step at a time, allowing the network and or behavior to change one step at a time. Okay, and to do this, so it's actually it's a Markov chain that we're stepping through, letting the network change one step at a time with current changes dependent only on the current state of the network. Okay, so it helps to simplify this process a lot. Now, to implement this, we're going to take an actor-oriented approach, okay, or an agent-based approach, or an individual-level approach, and we're going to think about change from each actor in the network's perspective. How does that actor perceive the network? Which tie do they end up changing? Okay, and what we're going to ultimately do is figure out what rules actors are using to change their network, and those will help us go from time t-1 to be able to produce a network that looks like what we see at time t. We're not trying to produce or predict the actual network with the actual ties that we see at time t, rather a network that has the same characteristics as that tie. So we're seeing, in a sense, saying the observed network is one of many networks that could have occurred. We're trying to model the process that is most likely to have led to that network. I have a paper that is coming out in a volume on I don't even know what it's called, Jim. What's your handbook? A handbook. Right. Okay. So, but for the time being, you can check out not a preprint, but check out the chapter here. It talks a lot more about SIENA models in comparison to other longitudinal models. Okay. So for the remainder of this section, I'm going to go through a little bit about what the model is, how we estimate it, and really focus mainly on an example and some of the interesting things that we can do with this. Before that, I'd like to go through a script in R that walks through the logic of a SIENA model in what I hope is a far more kind of intuitive sense. Okay, so this is up on Dropbox. I'm going to go through this. Let's see. Can you all see that in the back? Enough? All right. All right. This is using packages that I hope you already have. And we're going to use Samson's data. Samson did his dissertation in a monastery and did some interview with the brothers in the monastery. So we've got 18 brothers over multiple points in time, who they like, who they don't like, as well as a wealth of information. We're going to use information on the status, so their formal role in the monastery. Some are new, some are more senior, as well as who they like across 3 points in time. Okay, so we can look at the network, we can look at it at a couple of points in time, and all right, not horribly intuitive. We can also look at how it changed. I didn't realize that you could do that with an edge list. You can just subtract edge lists and figure out which change. Nice feature of edge lists in the network package. So you can see which ties are added, which ties are dropped. Not much to see here other than it happened. And if you know the story of the monastery, you know that there was a group that started to not get along, and people ultimately ended up leaving as factions were created. Okay, that part is less of interest for the story that we're going to tell. Our question is going to be simply, we start here at time 1, a bunch of ties change. How did we get to time 2? Okay, what is it that happened? What were these brothers doing? Okay, and so let's start by thinking about the rules that these brothers followed in changing their ties. Okay, so keep in mind, these are directed ties. This is for each brother, who they like. And let's say brothers are limited to the information on hand. Okay, so all they know is the network. Okay, they know who they're tied to and who else is tied. And they know their status, and they know someone else's status. Okay, everyone else's status in the network. Okay, so let's see if you've been paying attention this week. What kind of rules might individuals use, these brothers use? Yes.
If I'm friends with a brother and they have a shared friend, then I probably have to be the friend of the shared friend.
Okay, so something like transitivity is what it sounds like. Okay, so triad closure. Okay, so we've got some network-based rules that we could implement. So we could look at it, who are my indirect friends, and make those. Okay. What's one of the most common processes we see in networks? It's not even a network process, it's a dyadic process. Reciprocity. We've got reciprocity, another network-based process. Now we also know an attribute, right? We know status, right? How might status come into play? Hierarchy. So we might prefer to be associated with people who are higher in status. Okay, that might do something good here. So some kind of alter-based rule where we look to see who is higher in status and try to befriend those people. Okay, we could also flip that around, right? So egos who are higher versus lower in status may be more willing to like or not like other brothers. Okay, and then a dyad-based rule, right? Homophily, right? We might prefer to associate like others who are like ourselves, who are in the same role and kind of going through the same kinds of parts of training, who've been in probably similar amounts of time as we are. Okay, so we can come up with all of these different rules. The model's great for how do we parse between all these rules, right? We've got 5 hypotheses already. We could come up with a lot more if we wanted to. All right, so how do we parse between these? Okay, so what we're going to do with the SIENA approach, okay, and we're going to start very, very simple, right, because this is just a conceptual overview, is let's say that our hypothesis is brothers prefer ties to high status or higher status alters. Okay, how do we test that? So let's create a model that follows that rule. Okay, let's take the network at time 1, okay, and we're going to allow it to change one tie at a time. How are we going to do that? So we're going to just randomly pick brothers. Okay, randomly pick one and give it the opportunity to change its ties. Okay, how does it decide which tie to change? Okay, well, we're going to have each brother look across the network and consider all possible ties. If there's a tie there, it's going to, do I keep it or do I not keep it? If there's not a tie, do I add the tie? And then that rule is informed by whatever effect is in our model. In this case, it's alters status. Okay, so brothers look across everyone else in the network. If someone's higher status, they're going to be a little bit more likely to be added than someone who is less status. Okay, and then in the case of ties, we're going to add a little bit of randomness to our evaluation. Okay, are we all together? All right. All right, we're going to be so we're going to calculate a statistic here. Have I been doing this as I go along? Okay, it's all just been me talking, good. All right, we're going to have a statistic here called alter z, where z is behavior. And this is going to be a way for us to calculate the value of each potential tie based on the value of z. And again, our hypothesis is those who have higher values of z have more ties coming in, and so we're going to calculate how many ties that alter has coming in based on and multiplied by z status. And this is going to allow us to we're going to use this when predicting or calculating the value of each alter. We're also going to use it to help evaluate fit later on. Here are a few more statistics that we could use. We're not going to use them just yet, but they're in there just in case. Okay. All right, so let's set up our model. We're going to create a few objects here. things that aren't going to change, but we need to know. Okay, we're calculating the number of changes in the network, so how many ties actually flip from time 1 to time 2, and we're going to use that to determine how long should our model run. How many chances should we get people to change their tie? Okay, we have 18 folks in the network, and we have our behavior here. All right, we're going to set our initial value of alter attractiveness based on this behavior, based on status at 2. That's just a starting point. Okay, and then let's create our network X. All right, and then we're going to run a model. We're going to use a loop here. And what the loop does is it's going to go through all 42. It's going to go through this 42 times. Each time, randomly select an actor. Okay, and then it's going to have that actor calculate the utility for each of those 18 dyads, excluding the tie to itself. Okay, so it's going to calculate the utility based on what's in our model, which is just that alter Z effect right now. Okay, so we're going to go through all 18 alters for person I, go to the next person, let them go through all 18 alters. After each person evaluates all 18, we're going to flip the one that's got the greatest utility. Okay, so you want this helps. Let's just do this I equals 1. Let's just do this for one person. Okay, so we've got an I. Let's create this utility function, and then we're going to go through all 18, and we could look at this utility. It's a bunch of numbers. If we plot it, we can see, okay, one of these has much higher utility than the others. Okay, that looks like it could be tied to oneself, which it shouldn't be. No, we've excluded the tie to itself. Okay, so J, that makes sense. J, I think that's J2. We're looking at I equals 1. J2 is the most attractive because J2 is higher in status. They're ordered by status. Okay, so that's the basic idea. When we run this, if we look at these, what are we going to see? All right, here's our original, should be our original network. Here is our simulated network. How does that look? I heard someone groan. Yeah, it looks awful. Why is that? There's too many ties, right? There's a lot more ties than what we want to see. Okay. Actually, we should be comparing this to time 2. But I can tell you already, it's going to look quite the same. Okay. So we've got way too many ties. All right. And so is this a good model? Well, we want a model to be able to produce this similar number of ties. We also want it to be able to produce what we're telling it to reproduce. In this case, how attractive are alters based upon that their status here. So what we can do here is calculate the value of that alter Z statistic, which is really in degree times alter status. Okay, so if we calculate that statistic, our observed statistic is right here, 166. Okay, that's multiplying status by in degree. Okay, so that's what we want to be able to reproduce at time 2. We're producing a statistics that's more than twice as high. Okay, so we're producing way too much, way too strong of an association between these two, way too many ties as we saw with that. So, all right, so our statistic is too high. We're producing too much. So what can we do? All right, so within a SIENA framework, what we're doing is we've taken a provisional value of 2, we've let the model run, and we're getting not quite the structure that we actually observe at time 2. Okay, so let's alter our parameter. Let's adjust our parameter. Let's drop it in half. All right, let's drop it down to 1, and then rerun our model. Okay, we do that. We're still getting way too much, way too strong of an association, way too many ties here. Okay, so let's drop it down further. All right, this is where we're happy to have computers doing this for us. Okay, drop it down to, we went from 2 to 1 to 0.1. We're still getting way too many. Okay, let's drop it down even further, 0.001. Okay, that's the weight we're giving to, again, higher status versus lower status alters. It's almost imperceptible, right? But if we do that, drop it way, way down, we're still getting too strong of an association here. All right, so what's happening here?
Not the right parameter to be considered.
It's a horrible model. Yeah. It's a good parameter. We don't have enough, right? There's nothing to stop people from adding ties here. Okay, people are just finding out who has the highest value on this alter status statistic, and even if it's just a little bit higher than somebody else, they're going to add that tie. So there's nothing to keep people from adding. So what we need is what's called an edges statistic or an outdegree statistic. It's edges in ergoms, outdegree, and others, but some way of penalizing ties if people get too many. Okay, so in essence, we've fitted a model, and our model estimation is coming up with parameters that it would actually explode with this specification because it doesn't work. Okay, so let's add another effect. Let's add an outdegree effect and keep our value of 0.1, give our outdegree effect of -2. So what this is saying is that adding ties is costly. Okay, each additional outdegree, each additional tie added is going to decrease the value of this function by 2. Okay, so that's a pretty big penalty. And let's run the model, calculate our statistics. We're going to calculate this time both. Our alter Z statistic here looks a lot better. Our density statistic, though, is a little bit off. Okay, we're not creating enough ties. Ties seem to be going to alters a little bit better, match to the observed distribution, but we don't have enough ties. Okay, so we're still not quite there. Okay, so what we really want to do is then go through this a number of times to get better estimates that get us closer. Now, we're going to do this a little more efficiently. We can create a function to do a parameter sweep, right? To look at a range of values for each of these. Okay, and then track the fit for each of these. So I'm creating a function here. This is the point where you're not able to follow me, I imagine, and that's okay because you can come back and look at this and find the bugs that I created, bugs that I left. But we ran a parameter sweep that looked at values from -2 to 2 for this alt Z parameter, from -2 to 2 for this outdegree value. Let's do a factorial combination of all of these, look at all these values, and calculate the fit for all of those. Okay, so if we do that, it runs remarkably fast, much faster than our SIENA models will. Now let's look at how well this fits. So I'm calculating some fits here by looking at how much the actual predictions from our simulation compare to our observed values, doing some things to standardize these so it's a little bit prettier to look at. And then let's plot this. Okay, so this is how much this alter status deviates, the count of that statistic deviates from that observed, standardized, and then for each value of outdegree and for each value of alter Z. And here, what we're looking for is the smallest deviation. Okay, we want the smallest deviation of simulated from observed. Okay, that's telling us their model's getting close. We see that that's down here, this region here, where outdegree is slightly negative and this alter Z statistic is positive. Those parameters are giving us the best recreation of this alter status statistic. Okay, that's one criteria that we can use to evaluate fit. Another criteria is how well are we able to reproduce outdegree, or the degree distribution. Okay, if we look at that, we see this kind of little weird structure here, but we see that some of the lowest values are here, where outdegree is negative, and alter Z is positive. And there's a little region here as well that produces reasonable fit. Okay? Now, ideally, our model is going to be able to recreate both of these. Okay? So we should be looking at both of these in conjunction. And that's what this last step here is plots the combination of these two. Okay, and when we do that, we see the best fit comes from parameters where outdegree is negative and alter Z is positive. Okay, yeah?
So we want to look for the deviation from the observed that's the lowest, so that like yellow color, not where it should be 0.
Right, I standardized these. So zeros turn out to be a negative, which I should standardize them in a different way. Sorry if that's confusing. This was last night, so if you have a better way to standardize, let me know so it's more intuitive. But yeah, zeros are going to be the smallest z values here. Okay. All right. Is that a question or?
Yeah, just a quick question. So isn't I'm reading the plot right? If I had just looking at this, if I were actually doing it this way, wouldn't I want to go further along on that z statistic? Because the optimal region is there popping out of my range, so perhaps it's 2.2 as I want.
Good point. Yes. We would continue exploring much higher. Yeah. Great point. Okay. So we've just run a SIENA model. Okay. Not a very good one. Probably a 90s era SIENA model. But that's the logic that the SIENA model uses. We're going to postulate a model, and then we're going to seek to find parameter estimates that actors can use following that model to recreate what we observe at time 2. Okay. Oh, just for fun, we've got a real SIENA model here that we can run. That's Siena, town in Italy. All right, so if we actually run this and look at the results, we do see that we get an outdegree effect that's negative 1.2, alter Z effect that's slightly positive. We'll talk a little bit more about how to interpret these in a little bit, but we actually see that this crude estimate actually gets in the right quadrant, so to speak, of effect and their estimates. Okay. All right, so I want to get back to get out of R now. Are there any questions about the intuition behind SIENA? Okay, because that's the most important thing to grasp right now. It is an actor-oriented model, so it's nothing like regression, nothing like an ergom. It's got this actor orientation. That's going to kind of influence everything that we think about SIENA models, how we interpret them, but also when we're estimating the steps that we take and how we evaluate those steps as we go along. Okay. All right, so then, all right, so I've got, let's just do this. Okay. All right, so I'm going to breeze through these because we've covered some of this. SIENA actually stands for something, Simulation Investigation for Empirical Network Analysis. That is a way that you come up with the name of a software that matches the town that you want to name it after, because that's the first place you ever presented the model. So that's why it's called SIENA. It's also called more currently, it's actually a stochastic actor-oriented model is what it's referred to more so in the literature. That's the model, whereas SIENA is the software used to estimate the model. Okay, so with the SIENA or Zaum, what we're trying to do is estimate effects of network on behavior, effects of behavior on the network. We're also going to be able to bring in some individual attributes, maybe some contextual attributes, and look at how those affect both behavior and the network, as well as looking at how the network itself affects itself over time. Okay, so we're going to be doing a lot of things with this model. Okay, to do this, it's an agent-based model. Okay, we're looking at these micro steps between our observations, And our rules that we actually use can be classified into these four types. Okay, so for the network evolution, we have a network rate function. Okay, so this determines how we choose the next actor to be selected. Oftentimes, we just let this be uniform, and we're selecting actors at random. But there may be times when we want to give some folks in the network more chances to change their ties than others. Okay. Oftentimes, someone new to the network might be more rapidly changing their ties than someone who's been in the network for a little bit longer. Okay. The decision rules are specified in this network objective function. So that's really where much of the thought goes into how to specify a model, is what goes into this network evolution function. Okay, we also have a behavior evolution function. Okay, so we've got like two equations here going on. Also, a rate function that dictates how often actors change their behavior. May be more frequent than they change their ties. Oftentimes, it's less frequent than they change their ties. Okay, these are both estimated by the model. And then we have a behavior objective function that specifies how individuals change their behavior once they're given the opportunity to change their behavior. Do they go up? Do they go down? Do they move closer to their friends? What is it they do? Okay. So this is the form of the network objective function. Okay, it's some function of current set of parameters and the current network. And what we're doing is summing across a bunch of statistics. Okay, these statistics are the alter behavior statistic we talked about, Outdegree, plus a host of other statistics that we think might affect which ties individuals choose. Okay. All right, so here is a more elaborate kind of example of how this decision process works. Okay, so here we have a hypothetical network, or a hypothetical network objective function specification. And what we're going to do is look at for ego, given a current set of parameter estimates and network, and this model with an Outdegree effect and a reciprocity effect, two hypothetical parameters, okay, -2 for Outdegree, 1.8 for reciprocity. If this is the network, these are the parameter values, and ego has the chance to change a tie, how does ego evaluate each potential tie, either adding it or dropping it? Okay? I'm not going to go through the math here. You've got the slides. You can look at how this equation gets filled with numbers. We calculate the utility of each of these ties, and then we're going to end up dropping J2, because across all of these ties, the tie to J2, it's not reciprocated, okay? So it's not producing any value that way, and it's costly to have a tie, okay? So why we have a tie to J2 if J2 is not providing anything back? Based on this model, that tie to J2 is worthless, okay? So we're going to drop that tie. Okay. All right, some of the effects in an objective function for the network, we always want to have Outdegree, right? That's getting at the probability, overall probability of observing a tie, keeps us in the right range there. Network processes like reciprocity, transitivity, we want to control for in-degree and out-degree distributions. So things like some people, there may be a popularity distribution where some people are much more popular and draw more ties, other people less popular and attract fewer ties. Those kinds of network processes, different kinds of attributes that might affect our behavior, particularly homophily, so being similar. And then we control for dyadic attributes, things that put people in the same context, bring them together, and enhance opportunities for relationships. Okay. All right. Now I want to talk about the behavior function. That's what you've all been waiting for, right? How do we predict how people change their behavior? Okay, we're going to call this behavior, but recognizing that this is really anything that can change at the individual level. Okay. Now, SIENA models don't really need one. In fact, the earliest SIENA models did not have a behavior function. They were really about how do we model network change. But it became apparent that it's quite easy, the model is quite flexible, and it's quite easy to add a behavior function or multiple behavior functions to predict how the networks influence behavior. If all you're looking at is behavior change, and you aren't looking at network and don't want to control for selection, you really shouldn't use a SIENA model because the behavior function is not as efficient as many other models. Okay, the benefit of the SIENA model is that it gets at this endogenous network change. It controls for a selection. Okay, but otherwise it's not great because until very, very recently, our dependent behaviors needed to be ordinal, coded as categories or ordered categories. Okay, and this has to do with the way that the model works. So the behavior function works similar to the network function, where individuals try to adopt different levels of a behavior. Okay, so they need to make these discrete choices between levels of a behavior. Okay, and so what I mean by that, okay, is we've got some function predicting, based upon some effects, what level of a behavior an actor will choose. Okay, so let's say we've got an actor who's at this level right now. They use this function to evaluate, do I stay at this level? Do I go up one level? Or do I go down one level? Okay, 3 choices, 3 possibilities. Okay, we're not going to go all the way up, or we're not going to go all the way down. With any microstep, it's just one change. Okay, we might keep going up across microsteps, right? If we're adopting a behavior that tends to be addictive, we might do that. But at any microstep, we're just evaluating these 3 choices. Okay, so these 3. Okay, so let's look at what kind of effects we have here. So we want to control for the overall distribution of the behavior, whether it's normally distributed, whether it's got some bimodal distribution or skewed distribution. So we have a couple of terms, a linear term and quadratic term, that help to control for that distribution. It also gets at things, so conceptually gets at things like some behaviors are addictive. So if you're at a higher level, you might keep getting higher. If you're at a low level, you might keep getting lower or stay low. Okay, so we can control for that kind of feedback of the behavior on itself. Okay, peer influence effects. That's the reason we're using this model, is to understand how others in the network affect one's behavior. There's multiple ways of specifying this. I'll talk a little bit more in a minute. But we could look at how alters value on the same behavior affects my value on the behavior. We could also look at how alters values on other behaviors affects my behavior. Okay, so if we're looking at smoking, we could look at direct kind of contagion or harmonization of smoking. It could also be something else about my friends' other behaviors. Maybe their drinking or their risk-taking more generally affects my smoking behavior. Okay, so we could look at these effects across different kinds of attributes. And then we can include controls for ego's own attributes that might affect the behavior, similar to what we would do in any kind of other modeling platform. We can then look at interactions between attributes and behavior, attributes and the network. We can get fairly complex here in what we do. We can also look at who's more susceptible. For instance, are certain kinds of kids, I study kids, right? Doesn't have to be kids, but certain actors more susceptible to influence from others for whatever reason. Okay, so here's a hypothetical behavior function, okay, where we've got linear and quadratic effects. Okay, so this is the effect of the behavior on itself. We have ego's attribute, okay, in this case ego's age, predicting, let's call it smoking, and then we've got a homophily effect. Okay, so a total similarity is one of the homophily effects, and so we're going to let this ego evaluate different behaviors based on this set of effects and their corresponding parameter values. Okay, and the question is, how attractive is each possible behavior given that this is the model that we're using? Okay, so we're going to model that over time. We can go through all the math here to figure out exactly how it is the SIENA model works. These effects are all pretty easy. Linear, quadratic, age. It's just looking at ego's attribute and each of the hypothetical behaviors and evaluating that utility. Similarity gets a little bit more tedious to calculate because similarity is a dyadic. It's dyadic, but then across all of one's friends. Okay, so the calculations end up being for any given behavior. If I want to maintain a behavior, I have to think about what that means for the similarity in each of these relationships, with only the relationships where I have a friend counting. Okay? So I do all this math for staying at my current behavior, and I get some value of this similarity statistic. All right, if I stay here, this is the utility. If I decrease my behavior, this is what the utility of that behavior is within this function here. If I increase to 2, this is the value of the similarity statistic. So notice decreasing to 0 has a similarity statistic of 0.9, as does increasing to 2. So those lead to the same value. The reason being that ego's at 1 and both of ego's alters are at 1. So either going down or going up increases the dissimilarity, makes ego more different. So both of those are offer less utility in terms of this dissimilarity. Okay, so that gets at this bigger notion that a SIENA model is not predicting which direction people move, and similarity is not predicting which direction people move. It's strictly predicting, does one move further, closer, or further to those one is tied to. Okay. All right, so we can plug in those numbers for the similarity statistic and then sum across, and we get the utility of each of these 3 potential decisions. Okay, and we see that the highest utility is over here. It's increasing behavior to the highest level. Okay, so going up. And we can see that across the model, what's happening is that the linear and quadratic effects, okay, those are producing what? 0, negative 0.25, and 0 if we sum those up. So those are saying the behavior has a distribution kind of like this, kind of a U-shaped distribution. People are kind of pulled towards the extremes, not super strongly, but okay. Age has a positive effect. Okay, so increasing age is more likely to be adopting the behavior. And then this similarity has this other kind of effect, right, where because alters are at this middle level, that's where ego is pulled. Okay, so across all of those, ego's probably going to jump up here. Okay, but that's not too far, it's not too different, and because there's a little bit of randomness added to each decision, it may be that ego just stays at level 1, at least during this micro step. Okay. This is why SIENA models take a while to run, okay, when we're doing these things. Okay, I'm not going to say much about rate functions. I want to make sure we get through these to get to what the more interesting stuff, the extensions and application. Okay, so I do want to point out that our SIENA model has 3 phases during estimation. When that picture of SIENA pops up, it's going to tell you what phase it's going in, and it gives you a sense of, should I wait around for this to end or come back next week? Okay, literally. Okay, so we're going to quickly initialize some starting values, right? Just some provisional values. And then we're going to go through phase 2 is a very long phase where we are estimating the model, we're kind of starting with the model observed at time 1 and letting it run multiple times, okay? And comparing the simulated counts at the end to what we observe and adjusting those parameter values. Okay, we do this a bunch of times, a bunch of different phases that try to get closer and closer to some good values. Okay, this is the longest part of running a SIENA model, is that parameter kind of, it's not a parameter sweep, it's a little, or a lot more efficient than that, but it's trying to circle in and find some good parameter estimates. Okay, once we do that and we found some estimates that come close to producing the observed network, then we're going to calculate some standard errors. So we're just going to simulate the model a bunch of times, 1,000 or 2,000 times, with a fixed set of parameters, and then use that final distribution of networks to calculate some standard errors. Okay, yeah, I'm not going to go through this, but as a model and as actors, this is what is happening. Okay, actually I lied. I'm going to go through it just briefly, enough to tell you that the decision to change your behavior or change the network is more or less random. It's based on this rate function. Okay, so all actors get a waiting time for network or behavior. So, and it's kind of like pulling a ticket. You go to the network change counter, grab a ticket. You go to the behavior change counter, grab a ticket. And then whoever's got the next number on either of those goes and gets a chance to change. Okay? So it's random, but one line might be shorter than the other. So you might be changing your network a lot more than you're changing your behavior. I guess it's one counter might be faster. That's what's happening. Okay. All right, so after we've estimated a model, we've got some results, two things we want to do. First, most important, check for convergence. Okay, so this is, was the algorithm actually able to find a set of parameter estimates that recreate the target estimates, the summaries of the network observed at time 2? Okay, we've got some statistics that we can look at in our output that tell us if, yes, we're able to get really close to those counts, at least on average, okay, without a whole lot of too much variation. Okay, if we've got convergence, this is similar to the degeneracy check in ERGM. Again, you want to make sure that the algorithm worked and is able to reproduce what it is you're expecting it to. Okay, and then we want to evaluate goodness of fit. Okay, so this is, again, very similar to the ERGM approach. We are calculating statistics, summary statistics that aren't in our model, and how well is our model able to reproduce those aspects of the network. Okay, so now I want to go through an example of an actual estimated model using AdHealth data. We're looking at friendship change and smoking change, and the emphasis here I want to emphasize is interpretation, what these effects really mean. Sometimes it's fairly intuitive, sometimes it's not, but there's some important caveats in interpreting these effects. This is actually using 2 waves at first. All right, so you can kind of think of the network function as a logistic regression, if that helps, but only in the sense that you're predicting a log odds. So you're predicting how a 1-unit change in your predictor affects the log odds, in this case of a tie versus not a tie. Okay, these are dichotomous networks. Okay, so tie presence versus tie absence. Keeping in mind that tie presence could be a result of keeping a tie or adding a tie. Okay, we're not differentiating between that right now. We could, but we're not going to. So it might be keeping the most valuable tie. It might be adding the most valuable tie. Similarly, kind of the counterfactual is that we are dissolving a tie or we're not going to add a tie. Okay, so in interpreting these two, we're also going to, if we're interpreting a single effect, we're going to hold all other effects equal. Okay, assuming everything else about the network is equal, which may be possible, may not be possible. Okay, and if we can hold everything else equal and a 1-unit change means something, then we can turn that log odds into an odds ratio and talk about the odds of one kind of tie kind of being there relative to the odds of another kind of tie being there, which makes it more, helps with intuition and explanation. Okay. And then similar, the behavior function is looking at how a 1-unit change in predictor predicts the log odds of adopting a particular behavior relative to the behavior 1 unit lower. Okay, so we're looking at the difference between of 1 and the outcome here. Okay. All right, so here is a model we estimated. We have one rate effect here, which tells us that there are 2 time points, and we're looking at the rate of change between those. If we had more time points, we would have a rate effect for every period between observations. Okay, now the rate effect is the number of microsteps each actor is given to change their ties, which is going to be more than the actual number of ties that they changed. Okay, because on any given microstep, someone may not change a tie. Right? They might just keep the network the way it is. Okay, but that's the number of opportunities that each actor is given on average. I'm including here the statistic that's actually used to calculate the rate. This is helpful to understand what an effect is. You can go in and kind of start to pull apart the statistic to see what it's actually calculating, which is super helpful for some of these more elaborate statistics. I'm also including here, this is the the name used in R to refer to this effect. Okay, effects are referred to by name. Okay, so you'll see this is a way to, these are the actual effects that we used. Okay. All right, our Outdegree effect is negative. Okay, it's typical for SIENA models, just like Ergom's, and it means that there's some penalty adding a tie. Ties aren't just a coin flip, right? There's the likelihood of adding a tie is incredibly small. Right here, we've got some odds of adding a tie, or 0.02 times the odds of not adding a tie if everything else is equal. Okay, that's really low. So it means we're not going to add ties unless some of these other structures are increasing the odds of adding a tie. Okay, these other things are important. People aren't just adding a tie out of nowhere. Okay. The reciprocity effect here, adding a tie or keeping a tie that creates this mutual dyad. Okay, those are about 7 times more likely than adding or keeping a tie that does not create a reciprocal dyad here. Okay, so here our comparison is, again, adding a is who we're going to choose. Okay, we're going to choose you or we're going to choose you. It's not adding a tie. If we're talking about adding a tie, we need to consider changes in other statistics that would be affected by adding a tie, such as Outdegree. Okay, so here we're talking about we have a tie, we're just figuring out who that tie is to, and with that comparison, if it's creating a reciprocated tie, it's 7 times more likely than one not creating a reciprocated tie. Okay, transitivity, so here's our triad closure. Adding a tie that creates one additional triad is what, 1.68 times more likely than the odds of one that doesn't create that one more. Okay. Now, these days we want to also include an interaction between these two, reciprocity and transitivity. Those are both such strong effects, and they both, at least in friendship networks, but many other kinds of affective networks. So we want to control for the fact that these two aren't necessarily additive. Oftentimes, one of those is sufficient to boost the probability of a tie. We don't need both, so they tend to have when they're both there, their effects tend to not accumulate. So we often see a negative interaction. Okay, so I'm going to scroll through. This is an example of a degree statistic, okay, where actors who have more incoming ties are likely to draw additional incoming ties. Okay, so something like the Matthew effect, where those who are rich with ties tend to draw more ties over time. Okay, this is an example of a dyadic covariant. So it's another network. Okay, it's a network of who co-participates in the same extracurricular activities, and the value of whether or not any ego and alter are in the same activity increases the odds of them being a friend as well. Okay. All right, these are attribute effects, and their statistics. I think I'm going to skip through those and focus here on smoking. Okay, we're predicting smoking as an outcome. Let's look at how smoking drives selection. We see homophily in the form of the smoke similarity effect. We see smokers are a little bit more popular. Okay, now this is a case where similarity is really an interaction. Okay, it's how ego and alter are their joint value on smoking. Is it close? Is it different? So in that sense, you can't manipulate that without manipulating egos and alters smoking. Right? If we're completely similar and we want to compare that to people who are dissimilar, where you're manipulating both similarity, but you're by definition manipulating someone's smoking level as well. Okay, so because of that, you can't hold everything else constant and then just interpret these in isolation. Okay, so what we want to do is for each of these, these effects that all include smoking, we want to calculate their joint contribution to the value of a tie. And we've done that here. We've looked at each combination of being a non-smoker, being a smoker, each possible dyad, and worked out the math for how does, for each possible combination, how do these effects contribute to the utility or the value of that tie. Okay, and when we do that, we see that yes, there is homophily, that non-smokers prefer non-smokers, smokers prefer smokers. they don't. They're less likely to choose someone who's different, but there's some asymmetry here, right? Smokers have a little bit stronger tendency towards homophily and a little bit stronger avoidance of non-smokers, people who are different. Okay. Now there's some script for how to do this on the SIENA website that I'll point to in a little bit because I don't have the math here. Don't try to do this in your head. It doesn't work because these are centered, internally centered. A lot of the attributes, especially particularly those attributes that we're predicting the outcomes of, SIENA will center them. It helps with estimation. So they're mean-centered. So you have to adjust for that when you come to interpretation. Okay. All right, smoking function. We have a rate here too. Everyone's got about 2 opportunities to change their smoking behavior. All right. Our linear and quadratic effects, again, those are 2 effects that we have to consider in conjunction because increasing one's behavior affects both of those statistics. Okay, so we can work out the math here, taking our raw values, centering them, and then calculating the contribution to the utility, and we see that smoking really has this U-shaped distribution. Okay, people don't smoke, or they smoke more than half the month. Okay, importantly, what I want you to take away here is the fact that the linear and quadratic effects, these are not getting at direction of change directly. Okay, these are not getting at, oftentimes if we saw a linear effect, it would mean that people tend toward higher values. It doesn't mean that people necessarily increase. Okay, we're not directly predicting the direction of change that actors take. Okay, we're predicting where they end up. Okay, so someone might be at level 2 and stay at level 2. Okay, they might be at level 1 and actually decrease their smoking. Okay, so we're predicting changes and values that are more attractive, but not that actually people are changing in a particular way. Okay, so we've got some covariates here. Here we see that delinquency leads to higher levels of smoking. We can calculate the odds of that. But when we do so, we need to take into account the linear and quadratic effects because anytime one increases one behavior by 1, that affects these 2 linear and quadratic effects. Okay, right? That U-shaped matters. So if I'm a delinquent and I'm going from 0 to 1, thinking about going from 0 to 1, okay, that difference from the linear and quadratic effect is also affecting my decision. I can't just look at the effect of delinquency here. Okay, average similarity is our measure of peer influence. And here, again, I mentioned the equations get a little more complicated here. Basically, what we're doing is we're calculating the similarity of within each dyad. We're taking the difference between I and j, subtracting it from the maximum amount of dissimilarity, and dividing it by its range. This is turning it into a variable that ranges from 0 to 1. Okay, 0 is maximum dissimilarity, 1 is maximum similarity. Okay, that's why this effect is so big, right? Because we're thinking about going from completely dissimilar to everybody to totally similar to everybody, which is the most one person can move. So most changes are not moving the statistic that far. Okay, but so we want to be careful about interpreting this as the odds of increasing because that 1 unit change is really a pretty drastic 1 unit change. Okay, I'm going to, in the interest of time, really skip through goodness of fit and show you that I actually got a good fitting triad distribution, so triad census. So there you go. I really want to talk about extensions. There's so many different ways we can extend this model. It's super, super flexible. And then show some examples of some of these. And I'm going to try to take a break and in 15 minutes or less. So, okay, so in a recent paper that may not be so recent now that I think about it, we questioned the assumption that peer influence is symmetric, that peers are just as likely to bring one down in behavior as they are to pull one up in behavior. Okay, and our hypothesis here, looking at smoking, was that friends kind of get you into trouble, right? They pull you towards smoking, get you to try it, but they're not going to be very helpful in getting you to quit because a lot of other things take over once you start smoking. Right? Once you start smoking, you know how to not smoke. You've done it. But it's hard to, right? Because addiction and other kinds of things make it hard to decrease no matter what your friends do. So we wanted to test that. Okay? So what we did is we relaxed the assumption that increases are the same as decreases, and we ended up specifying a separate behavior function, one that only considered increases and one that only considered decreases. Okay, so when it came time for, right, in the model, actors are trying to decide, do I increase? Okay, let me look at this function and these parameter estimates for increases. If I'm considering decrease, let me look at this function. Okay. All right, so this is an attempt to try to explain what is happening here with these in these different scenarios. Okay, so here we have an ego who's currently a moderate smoker, right? They're right in the middle. There's a U-shaped distribution. They're not going to stay there. Which way are they going to go? Okay, let's say all of their alters don't smoke. Okay, in which case, ego could stay at 1, could jump down to 0, could go up to 2. Here's the utility of each of those. Okay, so here in Jefferson, we see ego's likely to not be a smoker, less likely to adopt smoking. In Sunshine, the other high school that we looked at, it's a similar kind of pattern. When ego's alters are all smoking, okay, these are all smoking at the highest level, then we see this distribution where in Jefferson, ego may jump up and become a smoker and still has a kind of smaller chance of not smoking. In Sunshine, it's a little bit reversed. In Sunshine, ego's still less likely to be a smoker than to jump up to smoking, okay, but can move in both directions there. Okay, so here we see what looks like differences in that, again, jumping into smoking is not something that happens when friends don't smoke. It's only when friends are smoking that there's a chance of adolescents jumping into smoking. Okay, and we could do this for not just ego being a moderate smoker, okay, which is these two, but we can consider if ego's a non-smoker, what the likelihood is based upon, here's an ego with non-smoking friends, and that we're not going to start smoking here. We're just not, right? It's only when a non-smoking adolescent has friends who smoke that you really see, okay, yes, there is a draw towards smoking. Okay, and by contrast with smoking, here we have ego who's a smoker, alters are a smoker. You see there's a chance of staying smoking, but there's also a good likelihood of, or a good pull down to being a non-smoker. Okay, so there's a chance that egos will be pulled down as well. So, which in this case is kind of the opposite of peer influence, right? This is becoming dissimilar to one's friends, okay, which suggests that some people quit even though their friends keep smoking. Okay, so this was looking at kind of questioning the assumption that behavior change is different for increases versus decreases. Peer influence is different for those two. We could do the same thing for the network function. Okay, there's lots of reasons to think that adding a friend is different from dropping a friend, right? That those processes are likely very, very different. So we could make that same distinction in a network function and test those effects. Okay. Now, the reason, or I guess I should say a beauty of the SIENA model is that this agent-based model foundation allows us to do a lot of things that agent-based models can do. Okay, and a lot of reason people use agent-based models is because they can manipulate things and look at the consequences, right? Things we can't manipulate in the real world. A benefit of SIENA in that regard is that we can actually fit a SIENA model to observe data, get some good estimates of what's actually driving network change what's driving peer influence, and then use that as the basis for simulations that tweak things that we're interested in. So we have, rather than just some kind of abstract theoretical ideas of the importance of these things, we actually have something that's empirically grounded. Okay? So one of the things we can do is we can ask, what would happen if selection were absent? What can happen if peer influence were absent? How much, and use that to try to partition how much of the observed similarity we see on things, in this case smoking, how much is due to people selecting similar friends, how much is due to peer influence. So we can partition that. So when doing that with, in the current study, we see that 40% of selection, of that homophily on selection is due to, or homophily on smoking is due to selection, a little bit less is due to influence. Other studies, I think all of these are using European data, find similarly that selection accounts for a little bit more of the similarity, some of the homophily we see than influence. Okay, so that's one thing we can do. These results aren't surprising. Oftentimes it is a little bit of selection and a little bit of influence. Occasionally you see just one, but oftentimes we do see a little bit of both. Okay, we can also use simulations to think about interventions, okay, and what might be the consequences of different kind of structural interventions. Okay, so here, this is a paper. This is a kind of a proof of concept paper saying let's use SIENA and manipulate some things and see what our outcomes are. So what we did is we manipulated the rules that actors follow. We manipulated the peer influence rule, so how influential are peers, and then how popular are smokers. Okay, so this is on the behavior function, this is on the network function. Okay, and then we kept everything else at its observed value. And we started with that time one network and manipulated these parameters across a range of values. For peer influence, we went from peer influence being 0 all the way up to 6. So 0 is no peer influence. We didn't do negative peer influence. I haven't seen that until I talked to Brian Aronson, who somehow has some negative peer influence effects he's trying to figure out, and it's baffling. We rarely ever see peer influence. That's an actual negative. Okay, so we manipulated peer influence to be absent versus very strong. We manipulated popularity to be negative, so smokers are unpopular relative to smokers, all the way up to smokers are much more popular, with the observed values being here in the middle. Okay. All right, and here is our results in a single slide, right? So here we are manipulating peer influence, holding alter popularity at its observed value. We see peer influence manipulating it really has no effect. Okay, whether peers are influential or not has no effect on, this is, the horizontal line is the observed time to smoking prevalence, and we're looking at how our simulated prevalence is distributed around the observed, so deviations here. Okay, so smoking alter parameter, by contrast, had a super strong impact. Okay, when smokers are unpopular, our simulated prevalence is much lower than what we actually observed. When smokers are popular, we see the opposite. Okay, the idea, here is fairly intuitive, I think. When smokers are unpopular, they don't have friends, right? They can't influence many people at all. So of course they're not going to. Only the non-smokers have ties and are exerting influence through those ties. Okay. Now here is looking at these jointly, and the bold lines indicate these values right here. And you see the same thing. When smoking popularity is at its observed value, peer influence really doesn't matter. Okay. When smokers become unpopular, actually here I think is the negative. When smokers become unpopular, peer influence has an effect, kind of amplifies that unpopularity. Okay, when smokers are unpopular and peer influence is strong, it means that those non-smokers are really exerting heavy influence on everybody else. So we go towards very low prevalence. When smokers are popular and peer influence is stronger, we see much stronger or much higher prevalence of smoking. Okay, so it tells us, here in thinking about manipulating something, we might want to think about how, again, the other processes that are at work and bringing people together in this network. Okay, now this is very, very crude, right? Manipulating just a couple of parameters, and I imagine many of you can think of more sophisticated kind of interventions, targeting specific individuals, targeting groups of individuals. You can think of a lot more things, but here I think shows that we can take this model and very simply extend its implications. Okay, now for this simulation, we just used Jefferson High School. Okay, and Jefferson High it's not a typical high school. Okay, so here is 95 of the ad health schools. Okay, and this is the prevalence of smoking in the last 12 months. Okay, so 0 up to about 55%. Anybody besides Jim know where Jefferson is on here? You have the, oh, I forget. See, all right, we're right here. Yeah, Jefferson is, I don't know, there's not much to do. Jefferson is it's a suburban school in the Midwest somewhere, and there's just not much to do besides smoke and drink and the things that go along with that. So yeah, so the question is, does this apply at all? Do these implications apply anywhere at all? How much does, really the implications depend upon the context? So what we wanted to do is start to answer that question. And so we did the same kind of experiment. So this is with Jimmy that you all met the other day. We did the same kind of experiment, but we used all of the ad health schools. Okay, at least as many as we could. Okay, we manipulated smoking prevalence, and then we spent a lot of time figuring out how do we distribute smoking within a school. Can we just randomly assign some people to be smokers or not smokers? We were a little wary of that because of things like this. Okay, here's smoking prevalence in a school, and here is homophily on smoking, and there's kind of a linear trend here, right? So when there's more smokers, there's more clustering on smoking. Okay, so there's this association between the network and the behavior that could be important. Okay, similarly, it's harder to see here, but in high schools, smoking prevalence is associated with smokers being more popular. In middle schools, it's the other way around. Okay, higher prevalence of smoking, smokers become less popular. Although I said that the wrong way. In middle school, smokers are popular. In high schools, they're not. Okay, so we want to be kind of wary, or at least take that into account. So we did a few things. We randomly assigned smoking values. We used an ergom to try to understand how it is that smoking is associated with being popular, sending a lot of ties, homophily, and then kind of keeping the same networks with the same, so we simulated networks, but also kept the same density as well as these other things. And then we just chose what in some ways is kind of the easiest thing, turned out being the easiest thing, is let's just take this distribution of ad health schools that has a range of prevalences and has the associations between smoking and network structure that we know to model, but also has associations that we haven't thought to model, okay, or that might otherwise be in the data and could be important. All right, and it turns out, let's see, this is our simulations using just the observed estimates, okay, and let's see, I think that is Jefferson High. So these are the parameter estimates from Jefferson High applied to all schools. Okay, we can't estimate a SIENA model on all of these schools because they only have one wave of data. Okay, if we could, we would do that. But these only have one wave of data. So all these other 94 schools just serve as different initial conditions to apply the model we had on Jefferson. So in Jefferson, we apply the model with the observed values. We get a distribution of smoking that's centered on the observed value. Prevalence doesn't change. When we apply this same model to all these other schools, we tend to see prevalence go down. Okay. All right, long story short, we don't see these three lines represent, you can see them here, represent the three different approaches. they don't differ a whole lot, except when in these really extreme cases where we have high values of smoker popularity and strong peer influence. We do see some departure. Otherwise, they're quite similar, which gives us some reassurance that in many cases it's not going to matter which approach you take simulation-wise. Key takeaway here is that depending upon the school, we do see very different effects. Okay, so for instance, take this scenario here, where we make peer influence stronger and we make smoker popularity stronger. In half the schools, that's going to increase smoking prevalence. Okay? In schools that have higher than around 30% smokers, we're going to see more smokers. In other schools, we're going to see a decrease in smoking. So this is the same exact intervention, right? Boosting the values of two processes, very different effects depending on the context. So we want to keep that in mind when actually talking about applying interventions, and think about the context and which kind of context a particular intervention might be most useful for. And we think these kinds of approaches might be a useful tool to begin isolating and identifying those kinds of contexts. All right, here, so again, different context, only 25%, 75% smoke. Depending on which way you go, you're getting very, very different movement in prevalence. Okay, I'm going to stop here. Let us take a break before the lab. There's some information you can look at. In particular, the manual for RSiena is incredibly thorough in terms of how to use RSiena. It's 200 or 300 pages, I forget, but a super, super helpful source. So I'm going to make sure you all point to that. If you're interested in technical details, there's a link to the actual algorithms SIENA uses that I would also point you to as well. And let's take a break and come back, and there's a slightly updated script that I put up, or Jim put up last night for the lab session.